Good morning, everyone. Welcome to the Pico-Seminar series, which is a part of the Pico Electrodynamics Theory Network. So the aim of this theory network is really to explore the microscopic pico-electrodynamics phenomena inside the matter. And we are trying to bridge the gap between both theorists and experiments working in the topological electronic band theory, quantum materials, quantum optics, density functional theory, nanophotonics, and really to look into this picoscale electrodynamic fluctuations and the arising phenomena deep inside the matter. So we had several seminars in this series, which is live stream on the YouTube. And today with us, we have one of the first experimentalists who's speaking with us today, Professor Ricardo Decca from University of Indiana. No, Professor Zubin Jacob will introduce him. Thank you.
Great. Thank you so much, Satvik. We are very happy to have Professor Ricardo Decca with us. And I'm going to introduce him in a second. So in the meantime, Ricardo, please go ahead and check whether your screen sharing works while I introduce you. So just make sure that things will go smoothly. Excellent. So it looks really good. So I'm going to take the opportunity to once again kind of welcome him and thank him for accepting our invitation. Ricardo was instrumental in many important developments in the area of Casimir physics over many years. He is the department chair of physics and also the co-director of the Nanoscale Imaging Center at Indiana University, Purdue University, Indianapolis, which we also call as IUPUI. He obtained his PhD in physics from Argentina and subsequently also held a postdoctoral position at University of Maryland, College Park. So he has a very broad set of research interests, including near-field scanning optical microscopy, and also works on spectroscopic investigation of quantum systems, biomembranes, and as well as the search for new forces at the submicron range. And we will be handing over the floor to Ricardo very soon. But before that, I also want to take the opportunity once again to congratulate him and the entire team that he is leading and part of that has recently won the kind of prestigious Center for Quantum Technologies from the National Science Foundation. So we hope to interact in a lot more detail and closely in the near future, and we look forward to listening about quantum friction. So welcome, Ricardo.
All right, thank you very much. Thank you, Zubin, for the introduction, and thanks also for the invitation. Really appreciate the opportunity of talking to you today. And as I was mentioning before a few minutes ago, I prepared this to be a rather short presentation, and just the idea is just to generate questions and try to see what things spike your curiosity. So whenever you have a question, just go ahead and interrupt me. And I'm not checking the chat, so just whoever has a question, just unmute yourself and ask the question. So what I'm going to present is quantum friction, which is when you have two bodies moving one with respect to the other one in a vacuum, there is this phenomenon which is associated with friction associated with vacuum fluctuations. I'm going to be talking about that one, and actually how we could measure it. And so that is basically the core of my talk. But I also will give a rather brief introduction of the other measurements we are doing in the lab and the other systems we are working with. And as I was said, well, here is my name, and I'm at the Department of Physics at IUPUI, which actually soon will be IUI because Indiana University and Purdue University are finally splitting, and then within 2 years will be called Indiana University Indianapolis. So my list of collaborators, this is not just for this part of the work. This is my list of collaborators for all the work we have been doing in the Casimir and short-range interactions arena. For this particular work that we are doing here, I collaborate with the people from Buenos Aires, Fernando Lombardo, Paula Villar, and Lumira Biotti. And then the people working here at IUPUI are Thomas, Muchuan, and Patrick. And funding has been provided by National Science Foundation, the Department of Energy, and also, well, also Department of Energy through Argonne National Lab, with whom we collaborate. Most of the stuff that I do, actually, I will show you later on why we got interested in Casimir, but most of the stuff that we do actually had to do with gravitation. And so it's, I have Einstein's field equation there, and the part in red, if you wish, is purely classical. This is the Einstein tensor and the metric tensor, in which the dimensions are 4. And if you basically work at low densities, low velocity limit, then this is basically reduces to the known Newtonian gravitation between 2 point masses, and which says that, well, this is a standard expression that we learned early on, that it will decay as the separation between the masses square. But the main point is here is that everything is classical. And so Einstein introduced the cosmological constant. In principle, the cosmological constant arises from vacuum fluctuations, or it could be arising from vacuum fluctuations, and it is quantum in nature. And then on the right-hand side, we have 2 terms. One is the energy momentum tensor, which is quantum in nature. I mean, anything that is associated with mass is quantum in nature, and it is proportional to this the gravitational constant, which there is an issue with the gravitational constant, and then we are trying to also determine the gravitational constant, because there is this issue that newer measurements do not coincide with the older measurements, and then there is an effort, a few groups in the world that want to measure the gravitational constant. We are one of them. We are using a torsional pendulum, and we are with this torsional pendulum, we are doing 3 different modes to measure to try to determine the gravitational constant associated with the Newtonian gravity, if you wish. So the limit of low densities and low velocity limits. There are very many different models or theories that predict that this Newtonian gravitational could be modified either by a Yukawa-like interaction or by another power law. And our experiments, the experiments we use, are basically designed to test for this Yukawa-like interaction that you can see there on top of the graph on the lower left. And basically, this is parameterized with 2 parameters, which are alpha and lambda, where alpha is the strength of this new interaction, if you wish, or the correction to the gravity expressed in terms of the gravitational interaction, and lambda takes different meanings depending on the nature of the correction. It could be the size of the compactification if you're talking about extra dimensions. It could be the reciprocal of the mass of the interacting or the particle that is mediating the interaction if we're talking about a new interaction. The point is that what we do is we measure, we place 2 bodies in close proximity and try to determine if there is an interaction we cannot account for. And as of now, nobody has measured that interaction. What you measure is a signal which is compatible within your error bar, compatible with 0. And from that error bar, you extract new limit that says, well, in this yellow region, there could not be anything new that is not explained by Newtonian gravitation. So, but the point is basically that one, that we need to put two bodies in close proximity to each other. And I'm going to show you in a minute that then the background there is the Casimir force. So then we need to understand the Casimir force, and that is how my involvement with Casimir interactions arose. About this mass distribution, well, we are now starting an experiment just to see if this if we can basically prove if this gravitational interaction is quantum in nature or not. So we're just starting, but basically it resides, this experiment resides in cooling down a particle to the ground state in a harmonic oscillator, and then put it in front of a mass density with varies as a function of position, and just trying to extract from there what kind of interaction we have, if we can extract that that we have a classical interaction, or if it or does it is that quantum in nature. And this is a very, very ambitious experiment, and in reality we will have to iron out a lot of systematics in order to be able to observe what we're trying to observe. Going back to towards the topic of this talk, well, I said that before that we had to put these two plates very close together, and then what happens is that due to vacuum fluctuations, then the electric field and the magnetic field are in vacuum, the expectation values are very well defined, are equal to 0. However, the density is different from the energy density is different from 0, and in fact it is infinite. And but that is not a big deal, because in reality we don't measure energies, we measure energy differences. And then what happens is that if you have the two plates at a given distance, and then the two plates, and you change the distance, that energy difference is finite. And if you have these plates, a pictorial way of representing this interaction, which is actually incorrect, but it gives the right at least qualitative understanding, is you have these two plates. The modes inside the cavity are reduced with respect to the modes outside the cavity. So these two plates are actually pushed closer due to the excess modes that you have in the outside. If you calculate actually the force, which is attractive, then you find that the force per unit area decays as the separation to the fourth power, and it is the dominant force at the small separations. And if you have a separation of 10 nanometers, this pressure is actually 1 atmosphere. So of course it decays very quickly. So if you go if you increase the separation, this decays as 1 over the separation to the fourth power. And this force is basically associated with, well, it is the same force that the van der Waals interactions and the Casimir interactions have the same origin, these vacuum fluctuations. So these photons, that virtual photons appear and disappear, give rise to this force. And if we have, for example, an interaction that a photon that appears interacts with matter, and then it excites a dipole inside the matter, and that information travels to the other piece of matter, and then it excites a dipole and then comes back. Is that a time of that time it takes for the information to travel back and forth? Your initial dipole is still present. The fluctuation induced in the first material is still present. Then we call it van der Waals, and it is a non-retarded. If the time it takes, if you increase the separation, in the time it takes to go, the information to travel back and forth, the initial dipole has already decohered. Then we call it retarded, we call it Casimir, but the physics is actually the same. Both van der Waals and Casimir have the same origin. Now, what we are interested in now, we have done extended measurements of the Casimir effect, but what I want to touch on today is something different. Now, what we're going to do is, instead of having these two plates stationary and measure the force, what we're going to be doing is we're going to have, instead of a plate, we're going to have a particle moving on front of a dielectric material. In order to, when you have that, the dielectric material, what happens is that then you have an image of your fluctuating dipole, and that image is retarded with respect to the position of the particle, which is moving with velocity v with respect to the surface. And since it is a little bit lagging behind, then there is an interaction. which is along the line of the two of the dipole with the image, and that interaction has two components, which is perpendicular to the surface, and it is more or less the standard Casimir-Polder interaction, and the other one which is opposite to the direction of the velocity. So in order to maintain the system moving at constant velocity v, this clearly is a non-equilibrium process, and this non-equilibrium process, well, you have to keep pushing your particle at constant velocity in order to sustain that velocity. If not, this frictional force will decrease it, or will decrease the velocity until it goes to zero. Now, a few things that are important to figure out here, and this is the key of the question. This idea started in the 70s to see quantum friction, got traction in the late, around 2000, 2005, and so on. And then there was a lot of activity starting in 2010 with discussions on how this force should depend both in the velocity and the separation, and then I'm going to try to convince you that try to measure that force per se is very, very difficult. For example, if you have, instead of having this particle in front of a plate, if you have two plates, one moving with respect to another one, the force, excuse me, I'm nursing a cold, so excuse me for the coughing. The force, the dragging force, the quantum friction force between two plates, if the plates are moving at a tenth of the speed of light with respect to each other, is 100th of the Casimir force, and it decays very quickly with the velocity. And in the case of this plate, the expression that decays as 1 over the separation to the 4th power. In the case of a particle, in front of the plate, after reasonably long discussion that I was mentioning before, this force is understood or to change as the velocity to the 3rd power, and decreases as the separation to the 10th power for a point dipole. So the decrease with the separation is very, very fast, and you have to then put this particle very, very, very close to the surface in order to have the hope of see any interaction with the force. But even in that case, if you do the calculations between the force that you have between a dipole or a nanoparticle that has a dipolar moment and this dielectric material, in the best possible conditions, you get forces which are, for velocity, which are in the order of 100 meters per second or so. You get forces which are going to be actually very small. They are on the order of 0.1 attonewton or so. And state-of-the-art measurements of forces are not quite there yet. So we have been trying to see if we interact with other people, Francesco Travai among them, and Karsten Henkel, to see, well, if that force can be improved. And there have been suggestions from the theoretical side that yes, there could be still enhancement if you pick your materials wisely, but still the enhancements are not very promising. Instead of being 0.1 attonewtons, you might have a few attonewtons, but still they are not in a range that we can measure. Fortunately, the collaborators from Buenos Aires came up with a different idea. They said, well, forget about trying to measure the force itself. What about if we look at the effects of this interaction, right? Remember, there is an interaction between the dipole and its image. What are the effects of this interaction on the phase of the state of the system? Now, what we're going to consider as a system now is a two-level system, and ground state, excited state. And you prepare the system in some superposition, and what we're going to try to measure now is what are the effects of this interaction on this phase of the system. And what they obtain is just by having a Hamiltonian. So you have a Hamiltonian that has the Hamiltonian of the two-level system is the first term. Then you have the Hamiltonian of the electromagnetic radiation, and you have the Hamiltonian of the interaction, which is just a dipolar interaction between this point dipole of the particle and the field, the electromagnetic field. So this interaction modifies the state of the particle. They do the time evolution of the system, or the time evolution of the matrix density with this Hamiltonian, and with terms which are associated with the fact that, well, we are in presence of a vacuum. It's an open system, so there are terms which are contribute to the dissipation, if you wish. So this modification is non-unitary because there are terms associated with this open system that are manifested in the system itself as a loss of coherence because we have these dissipative terms, or this flow of information from the particle to the reservoir, which is the vacuum. At any rate, if that is present but is not too strong, then in principle we should be able to measure the change in the coherent state of the particle as we move it in front of the surface, and that is what we intend to do. Here are some calculations that were done, and what I'm plotting here is the change in the phase at a given velocity. On the left-hand side is the change in the phase at a given velocity minus the change in the phase at u equals 0. So whatever the coherence or whatever effects in the phase you had when the particle was not moving on top of the plate, use that as a reference. And what it is plotting here is the changes on the phase as you increase, as you have a velocity, a relative velocity between the two. This relative velocity, in reality, this u is given in terms of course, is done in a-dimensional. The u is associated with the velocity, but also takes into account the separation between the particle and the plate, and also the properties of the material, which is in this case is just represented as through the model with a characteristic plasma frequency. The four curves that you see are a nitrogen vacancy in front of silicon is on N-type silicon is the top one. The ones that follows is a nitrogen vacancy in front of gold, and then also the calculation was done with a rubidium atom in front of silicon and in front of gold. And the conclusion you can see is that, well, nitrogen vacancy is better than rubidium, and silicon is better than gold in order to see this effect. And then the effects are significant. Bear in mind the scale is logarithmic here. So for an MV center in front of silicon, you can have an accumulated phase on 6.3 nanoseconds. This n is represents the time. At 100 in n is 6.3 nanoseconds. You can have an accumulation of phase which is close to 2 pi. So this is rather important. What you see on the right-hand side is how the density matrix changes, also the difference between the off-diagonal matrix element at 0 velocity and at a given velocity. So basically this is information of the loss of coherence. And you can see that again for the MV center in front of silicon, this is maximum. Now, why MV center and why N silicon? This is not exhaustive at all. MV center is a good representation of a two-level system, and the N silicon and gold are good materials to try, but it is very likely that there will be other materials that, in principle, will have better results than N silicon and MV center. On the other hand, the experiment that we're planning to do, well, we are going to start with this and try to see if our experiments agree with the predictions done by the collaborators. in Buenos Aires. Now, what we have to do now is we have here an MB center. So in diamond, so we have the carbon atoms, and then we have a nitrogen impurity and a vacancy associated with it. And then this has a dipolar moment along the MB direction. And this, when you put a magnetic field, this is effectively a two-level system, which is going to be given by the ground state, which is the M equals 1 in the 3A2. And the first excited state, or the excited state, will be the MZ equals to -1 in the same system. And then you can do purification of the levels by just producing luminescence of this, exciting the luminescence of this material, because when you go to the 3E, what happens is if you go from the M different from 0, it has an alternative path. It can decay directly to the same state, but it has an alternative path that actually what happens is it goes into an intermediate state that is more long-lived. And then by continually pumping this, then you can purify the state and put it in the ground state. So the experiment we're planning is then basically what we're going to do is we're going to put the MB center in close proximity to the material. And the material is going to be basically a silicon wafer, an end-doped silicon wafer. And then in order to keep them at a constant separation, we use AFM techniques. And then on top of that MB center, what we do is we do the optical manipulation and optical addressing, the standard optical manipulation and addressing with the corresponding microwave in order to see the transitions between one state, the ground state and the excited state. And then we have to basically, we are in the process of building these apparatus in order to produce the measurements. One thing that is critical in our experiment is to keep the separation between the MB center and the plate constant. And this has to be kept constant within a range of 10 nanometers. If you go beyond 10 nanometers, then since remember we expect 1 over the separation to the 10th power decay, so very quickly you don't see any effect, not even in the phase that we are trying to observe. Then what you're having here is we have seen that as we rotate the plate, we can keep the separation between the MB center at the end of the AFM tip and the plate to within a fraction of a nanometer. So there are two curves here. One is at about 3.5 nanometers, and the other one is about 7.2 nanometers. But we have to. This is not that the plate that is rotating is so stable. It has fluctuations in the height, and it also, the motor that we use in order to rotate has a small wobble, but still is significant. So what we have to do is, as the system changes the position, we have to track those changes in position with our AFM. And that is what is shown in here. So we're pretty confident we will be able to keep this separation constant. From the point of view of addressing the materials, then what we do is, well, you can take a look into the top panel represents the fluorescent lifetime of the 3E states. And you can also see that the light that is coming from the MB center is a single photon because you can do anti-bunching experiments. Now what we do with a microwave, we prepare the system, as I said, you can purify the system, put it in the ground state, and now what you do is you produce a pi over 2 poles, and let's say that you send it to the X plus X state, and then you wait a given time, and then you apply a pi pulse. So from what if there are no interaction, what will be the plus X will go to the negative X, and then you apply again, you wait again a time t over 2, and then you apply another pi over 2 poles and send it back in principle to the ground state. Now, the point is that when you apply the first pi over 2 poles, there will be some effects of the coherence, usually associated typically with the the fact that the carbon, you have different carbon isotopes in your diamond and they interact differently with the MB center, and that produces the coherence. So the purity of your plus X state starts to get lost. But then when you apply the pi poles, what happens is, and you wait the same time, is that has basically, then you play the movie on reverse, and whatever happened before associated with crystalline fields, for example, will actually recollapse the system, and then you can apply the pi over 2 poles and send it back, and that way you can measure these echo signal. Yeah. And then from there you can get the coherent lifetime of the system, and that coherent lifetime on these MB centers is rather long. That's why we selected an MB center. You get a milliseconds long coherent lifetime. Now, what we expect that is going to happen is that on top of this quantum friction, remember now we have this silicon plate which is rotating, and it will have, or any dielectric that we have, it will have patches on top of that. And so part of the calculations we are currently doing is, well, how will that affect the coherence? Because again, this will be a function of velocity. And so in order to characterize the sample, just to show you, we do AFM and then Kelvin probe force microscopy in order to see the potential distribution. What I'm showing here is just a gold-coated surface. This is not associated with silicon. This is a gold-coated surface, and then we have to do in whatever sample, whatever system we are going to be using, we have to do this, and from this, we have to extract what will be the influence of this effect. And the problem is that if you, for example, calculate the energy between two plates with a random distribution of patches, then you get another interaction, and that interaction is actually quite significant. The spectral function of that interaction could be, I'm putting here the horizontal line is 10 to the minus 15 newtons, so 1 femtonewton, and depending on the size of the radius, or the typical radius of the patches, then you are going to get different interactions, and these 3 curves are done as 3 different separations. So this is just to give an idea that these patches are going to play a critical role in also decohering the state, and that is what we're working. So I will stop here. I gave you a rather quick introduction to quantum friction, and then a little bit of the experiment that we're trying to do. We're trying to basically measure this quantum friction. We have no hope on measuring directly the force. Even if you try to measure directly the force, I show you just the patches will give us a contribution that is much larger than the force that we're trying to measure. But we're trying to see what are the effects of this dissipative interaction in the phase of the state that we prepare. We are using an MB center in front of N silicon, and as I said before, there is a lot of room for trying to improve it in there, but we are going to start with those. And of course, we have to basically go to the lab, build the system, and figure out what are the systematics. These fluctuations that we observe in the vertical position, will that also kill the results? What about the patch effects? How are we going to reduce the effect of patches? All these are questions, experimental questions that we will need to address. How to prepare the surface in such a way that the patches are not playing a significant role. And also it could be that instead of doing just do a spectral filtering and just measure one MB center, maybe there is some advantage into measuring a collection of MB centers all at the same time. So thank you for your attention, and I will be glad to answer questions.
Okay, thank you so much, Ricardo. This was excellent. And once again, I on behalf of the entire theory network, I want to thank you for your talk. So Satwik, you can now go ahead to stop the recording, and we'll start the informal session.